Let's talk about carbon for a moment. And in order to do so, it needs to be made, or I need to reintroduce to you the idea of the law of conservation of mass, which says matter is neither created nor destroyed. This means that the atoms in today's Earth are over 4 billion years old and will continue into the foreseeable future. The carbon in your body could have been part of a dinosaur or in a planet. And this leads us to something called the carbon cycle. This is this diagram shows the global carbon cycle, and it shows the way carbon atoms are distributed and moving around on Earth. The natural carbon cycle is a dynamic, steady-state system, which means it is all balanced. All these things are happening simultaneously. You see the arrows? But they're at different rates. And each and every carbon atom in the world has gone through this cycle 20 times. Every carbon atom has gone through the cycle 20 times. All living things are made of carbon, even plants. They're born, they live, they die, they decay. Animals, but mostly plants, did this hundreds of millions of years ago to form fossil fuels. Even rocks made with carbon form and decay. They dissolve slowly. Let's concentrate on the CO2. What's happening? To a lesser extent, more people means more CO2 from respiration. Deforestation, that's nothing new. The North America and Europe has been deforested since the 1800s and earlier. Another is the slow decomposition of plants. That also makes more CO2. Huge source of CO2 from the atmosphere, photosynthesis of plants. This brings CO2 out of the atmosphere and creates oxygen and glucose. So here's respiration. That's we talked about animals. The oceans are a huge reservoir of carbon. This G is giga, which means 10 to the ninth, so a billion. And this is tons, so that's 2,000 pounds. So we're talking over 1 trillion pounds there. That's a lot of carbon atoms. Most of the carbon is in carbonate minerals and fossils in solid form. You can see that I kind of wrote over it, but there she is. He's 10 to the 7th. And then there's a lot in the deep oceans. There's different amounts depending upon where it is. CO2 dissolves in the water. So we've got C atoms. That's what we're looking at their movement here. But when they get into the atmosphere, they are by far CO2. That's why you see it noted right there. Okay, this is a big wild card, the solubility of CO2 in the oceans, and it used to be felt that we would not have to worry about an imbalance of CO2 because the oceans would absorb so much, but that does not seem to be the case. We are building and building and building CO2 unnaturally in our atmosphere. Where do we get the CO2? Fossil fuel consumption. Utilities, that means coal burning, power plants. Right. We only have 3 fossil fuels. Transportation, that's gasoline. That's crude oil for the most part. And residential commercial, woo! This is, and maybe this a little bit too, is methane. This is burning of natural gas for heat. Over 80% of our heat in our homes and businesses comes from methane. Okay. All right. Deforestation, land use, we call it also, contributes another 1 to 2 gigatons a year of CO2 to the atmosphere. It's a lot. Okay. Let's do a little bit of chemistry here again, because in order to figure out how the carbon is Well, when we burn the fossil fuel, we can figure out how much carbon there translates into how much CO2 in the air. We've seen this a little bit before, but when we talk about chemical reactions, we're talking about bonds breaking and new bonds forming. Conservation of matter always is going to be in there, and this is how we look at it now. The number and type of atom must be the same before and after a chemical reaction. All right? That means we're not going to break down any atoms in this class, maybe in atomic physics, but not here. This is the combustion of methane. Notice that methane, we can look at it as one methane molecule, reacts with two oxygen molecules to make one carbon dioxide and two water molecules. And they've tried to draw them for you so you can see the shape. Okay. All right. Remember that that the oxygen in water has two lone pairs out there. That's why he's bent. And carbon dioxide is linear because it has that electron distribution. All right. Now, it's important to realize that the subscript here is much different than the subscript there. This is for the whole species. This is within the species. So this is telling me I've got two of these, and this guy is telling me I've got two total. So when I break it down to the atoms, she's got 4 hydrogen atoms and 2 oxygen atoms. And the reason why I emphasize this is because, look at this, hydrogen peroxide, that's H2O2, is a much different chemical than water. It would kill you if you drank it. When we balance these equations, we are going to look to see how we can make sure well, let's say the basis of balancing equations is the law of conservation of mass. The chemical equation must always include the same number and type of atom before and after the arrow. When we attempt to balance an equation, all substances must be represented by formulas that describe them as they exist. What I'm saying is you use O2, not O. And you never change the subscripts, and there's a little bit of trial and error in this, so just stay calm and don't worry if you have to go back and fix something you've already done. Okay. We look for elements that appear in only one place on each side of the equation. And then second, if free elements appear, you balance them last. Often O2 or H2 fit this, and whole number coefficients only. Okay, we have the best way to do these is to look for examples. And we keep doing combustion, so let's stick with it. Combustion is the burning of a substance and oxygen from air, which I've told you means O2, usually with a flame. We're going to keep with carbon, hydrogen, and oxygen. Then with sufficient O2, the products are always carbon dioxide and water. Okay, let's try balancing a chemical reaction. For example, how about this one? CH3O, CH3 plus O2 going to CO2 plus water. Okay. It is easier to visualize if we write the first species collecting the elements. So let's draw this instead as C2H6O. Good. All right. The carbon and the hydrogen are not balanced. Both only appear in one carbon on one compound on each side, so we can do either one. We've got a 2 here, so we're going to put a 2 there. Balance the number of carbon atoms. We've got 6 hydrogens, so let's put a 3 here. 3 times 2 gives us 6. Now balance the uncombined, the single element oxygen. You don't change the 2 there. Okay. We're going to come over here and let's count how many oxygens we have. Okay, here we've got 2 times 2, or 4. And then we'll add that to the 3 over here, so we have 7 oxygens total. How about on this side, on the reactant side? Well, we've got 2 oxygens here, good, 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 and 1 oxygen here. I really don't want to play around with the coefficient with this one. Why? Because then I'd have to change him, and it's just like a domino effect. So why don't we just say that we're going to do everything to manipulate oxygen right there. And we're going to simply take this out of the mix. So we're going to take 7, what we need, minus 1, and we're going to have to account for 6. Okay. Okay. We had 7 on this side. That looks like a 70, but it's just 7 oxygens. And now we need 6 on this side after we take away that 1. And how do we do that? We put a 3 there. This is a balanced equation. The 1 is usually not put there. It's understood. And now, the last thing you need to do is to make sure that you've done what you think you've done. So we count up each element on each side. And I've got 3 times 2, 6 plus 1, 7 oxygens. Yay! How about on this side? 2 carbons, 6 hydrogens, and then 4 plus 3, again 7 oxygens. We are done. Yes! Okay.